additive functionals of thermal processes.
Thank you. Where's the chalk? Oh, yes. So I would like to talk about limiting theorem for additive functional of alpha stable processes. So I would like to study such situations. So we have eta to gamma integral 0 to t f of eta set s ds. Eta goes to infinity, and we would like to prove something about the asymptotic behavior of such quantity. And Z is alpha stable. And of course, taking into account the self-similarity of Z, so law of Z lambda t is the same as the law of lambda 1 over alpha zt. Equivalently, we can study behavior of lambda gamma over lambda alpha minus 1 integral 0 to t lambda t f zs ds. Also lambda goes to infinity. Right, that's the same. And my talk will be based on two joint papers. First one is with Francesco Russo, and the paper appeared in Bernoulli in 2005, and the second will be published in Potential Analysis with Anna Talarczyk. And of course, there's a long history of limiting theorem for additive functionals. I think that the history goes back to the paper by Kalyanpur and Robbins, in 1953. There is and it was concerned with the case where Z was a Brownian motion and F integrable with unbounded. Then there is a Darling and Katz. Katz 7. There are plenty others. I think there are interesting results obtained by Bingham. And the case of Brownian motion is treated in Bingham, Goldie, and Tegos. In the book, there's also works by Kashahara, and of course Kipnis and Varada. So I will definitely I mismet the citations. So this is my primer object, but first I would like to say something about motivation. So motivation came from SPDE. So let me consider stochastic heat equation, nonlinear stochastic heat equation. So we have the U plus Laplace operator plus FU, that's dt, plus dw. And we consider it on some bounded region of in RT. So we have some initial valued conditions, 0, and of course we have boundary condition and boundary. And f is Lipschitz integrable or of trigonometric type. So like sinus, cosinus, fx is sinus x. So where is the problem? Of course, because it sounds very regular. Oh, W is a cylindrical Wiener process, and dimension is 2 or bigger. So W Wiener, cylindrical Wiener on L2, and D is say 2. Okay, so in this case, of course, the solution to a linear equation is a distribution value. So if we consider this process, dW, which is given by variation of constant formula, I will assume that Z0 is U0 for simplicity. So Zt is the T, that's the semigroup generated by the Laplace operator with these boundary conditions on U0 plus integral 0 to T e2 minus e2 T minus S dWs. And of course, this is not a function valued, it's a distribution. So U cannot be a function valued. It's also given by a variation of constant. It should be my this, so that would be zeta t plus integral 0 to t into delta t minus s f of us s. And of course, we have a problem how to understand this. I mean, how to extend the definition of f on the distribution. It turns out that the situation is much simpler than it looks. And this is what what is written in the papers by Albeverio Haba and Russo. I think it is 2001, and also by Guggenberger and Russo. Yes. So, what was the idea? The idea was very simple. I mean, very natural. It's to approximate W by something more regular. Say finite dimensional n. So instead of so the approximating equation was this: un plus f un dt plus dwn. Wn is an approximation of a cylindrical Wiener process, and they wanted to pass with n to the limit. And the question, of course, whether the limit exists or not. And it turns out it exists. So un converge. And it turns out that the limit is z. So the limit does not see this term. Of course, this is a distribution. I mean, what they prove actually is that if Zn is the linear equation, solution to a linear equation, Wn, they prove that supremum over T Zn minus unt to any power actually in L2 goes to 0 as n goes to infinity. So this is what they show. But of course, Zn in the space of distribution converge to Z. So in the space of distribution, un converge to Z, because not in this space. So Zn to Z in some h minus alpha space. So everything is very clear. And also what they observe is really that this difference is more or less so that nt minus unt is more or less the same as this to t e to delta t minus s f of Zns ds. So this is due to the Gromwall and Lipschitz property of f. So that's more or less this something which is comparable. Okay, this is a Gaussian process, and they look, and actually they prove also that if Z is any family of Gaussian processes with covariance in L2 going to infinity, they will obtain that this goes to 0. So it's not necessarily Ornstein-Uhlenbeck. You can multiply Gaussian variable by constant, and you will get the same. Okay, so when I visited Francesco, we wanted to recover f in a sense. And of course, we started to think about the very simple situation. I mean, not SPDE, but ODE. It should be dx eta is, say, f x eta dt plus eta dw. W dB. B is a one-dimensional Brownian motion. Yes. Okay, so it turns out that integral, for simplicity, we assume that this is 0. That doesn't make any difference. And it turns out that xn is more or less the same argument as here. It's the same, xn is minus eta bt is more or less the same as integral 0 to t. I should write f of x eta s ds. This is identity, but So this is the same, but this is more or less the same as this f of eta ds ds. So we have an additive functional of a Brownian motion. F is again the same as before. Okay, then everything should be clear now. Yes, if f is integrable, this is dimension 1, we have density occupation formula. So at f eta beta s ds is the same as integral over r f eta x. This is the local time Brownian x. We can change the variables and we will obtain s ds is the same as r f y L beta t y over n dy. I multiply by eta, and of course this goes to something, well, no, this is L beta t 0. That's trivial. Actually, that holds not only for a function, but only for a measure. So one can define the concept of the, one can consider ordinary differential equation with a measure. F is a measure in the drift. If the measure is finite, we have the same result. With a big effort, one can study fluctuation. So this is a law of large numbers. So if we consider this as ds minus s y t 0, and one should find a good renormalization, I mean good scale. We should multiply by something which goes to infinity, because this goes to 0 to obtain a non-trivial limit. So the correct rate is square root of eta. Then it converges weakly, of course, in C0 infinity R to some constant depending on f, and then there is a beta L gamma t0, and this is a Brownian motion calculated on a local time of an independent Brownian motion at 0. So this is, and this formula holds for f, a finite measure f with finite first moment. So with this. Okay. So that's, if f is integrable, everything is right. And of course, if we replace eta bs by x eta, we will get the same the same converter. Right. Now, what happens if f is trigonometric? Oh, this is much well known. It is, but I think that maybe not everybody knows it. And this is a nice calculation. And okay, So we would like to study this. I will take sinus or cos of sin eta ds ds.
What were your assumptions on f in the previous case?
In the previous case, f is a sine measure with finite total variation with the first moment finite. I mean, for the central limit theorem, for this I need this. Actually, I need less, but I need this. For the previous, I need only that f is a finite measure. Yes. But I mean, the previous was certainly well known. The fluctuations maybe not so known. And this is also known. Why? How to calculate this? We would like to maybe write this. I mean, with square. Then it's obvious what I would like to use. I would like to use eta formula. I mean, reverse eta formula. So I will write that this is what? This is sinus eta bt minus sinus eta b0, right? So I'm writing eta formula for this. So this is this plus, that's the, the second derivative is minus, so maybe I should change the sign. Then I have plus, minus doesn't matter actually it's minus integral 0 to t cosinus eta beta s d beta s, and of course time eta. Alright, now it's okay. That's up to plus or minus. Right, so if I divide it by eta, I will still have eta times this, maybe with eta beta s ds. Then that will go to 0 because I divided by eta, so it's not important. So this is more or less like this. Eta beta s d beta s. This is a martingale. And of course the quadratic variation of this, so I will denote by m eta t. So m eta t is integral 0 to t cosinus square eta beta s ds. And again, cosinus is 1 over 2. 1 plus or minus, doesn't matter now. Cosinus is also cosinus, but 2 eta beta s, right? I mean, and we go with n to infinity. That's integral 0 to t. This will be just a t, and that will go to 0. So it's like t over 2. So we can believe what is the right answer. The right answer is that eta integral 0 to t sinus and beta s ds converges weakly to a Brownian motion, of course, multiplied by some constancy. Yes, because the quadratic variation convergent. So that's the central limit theorem. Okay, and now the question is, what happens if we have a Levy noise, alpha stable? It's still for the Similar question. I'm looking for a. Seems that. Yes. All right. So. If f is integrable, then again situation is very clear. So now let set be alpha stable and first case f integrable. Why? So if alpha is less than 1, or in d-dimensional case, alpha less than d. So if d is 3 for all alpha, for d equal 2 for all alpha but not for a Brownian motion, then I will write in this way: eta alpha integral 0 to t f of eta zs ds in law is the same as integral 0 to lambda t, I mean, as a process, f of zs ds, and it converges to integral 0 to infinity f of zs ds, actually in c epsilon plus infinity. So for any epsilon bigger than 0, the point is that this converges. This is fine. So if alpha is bigger than 1, then there is a local time. I mean, this is dimension 1. Then there is a local time and of course what we will have that eta f of eta zs, which is converges to L set t 0. This is the local time at 0 integral of fx dx, like in the Brownian motion case. And this is in law. The process is the same as lambda to 1 over alpha minus 1 lambda t f of zs ds. Okay, so it remains only the case of alpha 1, and this is the same case as for two-dimensional Brownian motion. We have to use some logarithm to make this integral convergent. And this is the same result for the Levy's processes. I found it in the paper by Wojtecki, Gorostica, and Talarczyk. It is in SPA 2007, So this is alpha equal 1. But of course, this is not, maybe they were not, well, I was talking with Anna Talarczyk and she was not sure that this is new. So it was stated as a lemma. They couldn't find a good reference for this. So this is not a main result from this, but anyway, so it's something like log lambda t, the s, the s, and that again converges to some constant, depending on f, times a random variable, so exponential random variable. And again, they prove that the convergence is weak in C epsilon plus infinity R for an epsilon. Of course, one cannot take 0 plus infinity because this is 0 at 0. So one could have to separate from 0.
This is as lambda goes to infinity.
Yes, this is as lambda goes to infinity.
So what about t? The right-hand side is around.
I mean, this is a functional. So,
yeah, I know, but
so I'm.
Is the right-hand side a Prof?
It's constant.
So it's a constant. Okay, that's what.
It's like here. This is also does not depend on t. It's constant.
So that's the case of the Cauchy process, isn't it?
That's the case of the Cauchy process, exactly. And I think it's the case of the two-dimensional Brownian motion as well. I mean, the row is different, but the convergence is the same. Okay, so what happened in the trigonometric case? And that was, in fact, the subject of this paper with Anna Talarczyk. So we wanted to study the behavior of such additive function of alpha stable when f is of trigonometric type. So we didn't formulate it properly. I mean, the class of admissible f, at least this class, so we can do it for f of this form m, and that will be some aj e to I p j x, so this is x. Okay, that's, if someone's real, then okay, would be aj minus jx. And pj are non-zero. They cannot be, for constant, I will not get anything intelligent. And with this function, I associate a number c. It is for sum aj square pj minus 2. And what we proved that f eta zs add up to alpha over 2 ds converges weakly in C0 infinity R to square root of C times Brownian motion. So we have a central limit theorem. So it's well, we were not able to find this result in literature. I mean, explicitly written. Oh, but could be something similar.
For which alpha there?
For alpha n.
Anything.
For n. Actually, for 2 also, right? But because this is a Brownian membrane case, that's no. So alpha is 0, 2. For 2 also. Of course, if one prefers this language, so this is precisely 1 over square of lambda. That looks better, maybe, but because it's independent of alpha. That S, the S, that again, C, that T. So when I show this result, Stefano Olla is an expert in central limit theorems. Well, he said that probably one can deduce from the Kipnis-Baradan theory. I mean, the idea is to, in Kipnis-Baradan, was a Markov process on a compact manifold. So one can consider this, I mean, project this on a torus. And with a clever calculation, one can obtain this, maybe the same result. But what we can do, we can consider the case with m is infinite. And that's something which is much more difficult for the Kipnis and Baradan approach. Okay, so what is the tool, how to prove these results? How we present only the tools, I mean general tools, and I will try to convince you that this is a right scaling, that I should multiply by eta to alpha 2, not different. And that's not very difficult. And also, what kind of technology I can apply in such situations. So
if it's trigonometric, it's
Yeah.
essential to state your result.
yes, of course, I think in polygon
Only
Yes,
trigon.
also of this type, right? Actually, F should be a Fourier transform of a measure. It's again finite measure with atoms, and there are some complicated conditions. I mean,
For the case where m equals infinity.
yes, exactly. So I'm not very happy with this condition.
It's strange to believe that. I mean, it's so natural. I mean, because we get the time natural.
I mean, what is strange? This?
No, you mean that you use a sort of a trigonometric nature of f. But anyway, you should see your proof.
Well, it's yeah.
I mean, to me, it looks like one of the CLPs that you could get by a regenerative approach.
Well, in Kipnis-Baradan, there's a martingale approach. The idea is that they studied the case where this is a Markov process, this is an additive functional. In a sense, they compare this with a martingale. One should solve the equation, the Poisson equation. This is so. If we have a martingale with a generator, we should solve the equation F is, say, Lg. So no, yes, I'm looking for G such that I have that. And then I can produce a martingale, and then one should prove something about the quadratic variation, and that goes to a constant time t. So this is the technology. It's like in this this sinus case, because I more or less I use this idea.
Would you get a similar result with a periodic function that took values plus and minus 1, for example?
I haven't thought about this. Yeah, I don't know. No.
It would sort of be integrating plus or minus 1.
What would be the Fourier transform of this? See, I think this is for my. You will see why this is necessary. I can do a very simple calculation for f of this form. Why? Because, okay, so what is the general tools? The general tools are, maybe everybody, a lot of us knows this. So if I would like to prove that if I have a sequence of random elements, so are random in C0 infinity R, that's RT, that's not necessary, but R, and I have also a random element, X is also a random element. So in my case, would be the trajectory of this additive function. And I would like to show that xn goes to x. So what I need to check, I need to check that a finite dimensional distribution converge. That's first. And the second, that's exactly that xn t1, xn tn converges to the x t1, x tn. So that's first. And the second, the tightness. That the law of xn, the sequence is tight. Okay, so instead of tightness, I can, there are many tools to check the tightness. For example, if I prove something like Kolmogorov xnt minus xns to power, for example, delta less than k t minus s 1 plus epsilon, and this constant are independent on n, that is okay. I have tightness. Okay, so now how to prove this? If the limit is Gaussian. If the limit is Gaussian, it is enough to prove that the moments converge. All moments converge. I have, so for any, this is not for any random variable. We have example of a random of a such situation that the sequence converge in all moments, but not converge weakly. But if the limit is Gaussian, it is true. So what we really did, we checked this with power 4, and we proved that the all moments converge. Right. And now just the idea why the scaling is proper. So and how to calculate moments also, because it's the same. So the idea is, okay, I have to calculate this expectation of eta to alpha over 2, integral 0 to t, f of eta zeta s is s to power f. Right? And I have to be sure that at least that for Ln the limit is exists, and actually it must be the moments of the Gaussian. So in particular for odd n should be 0, right? Because the moments are 0. So f is the Fourier transform of mu. This is, I mean, we can see immediately in this case what is mu. It's a measure concentrated on these atoms. And what I will get with very simple calculation that this is n alpha over 2, that's clear, integral over Rn mu n dx, this is the, and I have integral 0 to t power n. Of course, I will write this in the sense that it is integral 0 to t ds1, integral 0 to ds2, and so on. But of course, I can integrate only on a simplex and multiply by n factorial. So I have n factorial integral 0 to t dt1, integral 0 to t1 dt2, integral 0 to tn minus 1 dtn. And what I have here is this expectation of e to e eta x1 z1 plus z t1 plus e eta x n z tn. So we have this. That's an absolutely elementary calculation. It's just a Fubini. We change the variables. So it's now I would like to use the, of course, I have expectation of this. These are not independent, so I would like to make them independent. So I will rewrite this form. So this is e eta eta x1 zt 1 minus zt2. But then I will get plus e eta x1 plus x2 zt2 minus zt3, and so on. Now I have independent increments, and I knew what is expectation of this. Because this is alpha stable, so that will be, in particular, this term will produce e to minus eta x1 to power alpha. This will produce eta x1 plus x2 to power alpha. And the last one, eta x1 plus xn to power alpha. Right? So this is the expectation. That's, oh, that's should, I should write something like with t, right? So I will write s1, s2, sn, and I change the time also. But anyway, I will get something like eta and alpha 2 integral r mu and dx time integral over some set t eta, okay, t, sorry. And this will be over ds, ds1, ds2. It's like a simplex. Actually, this is s, s1, sn, such that si bigger than 0 and some as I is less than 2. Right. So this is elementary. It's not everything actually here is elementary. Now we would like to pass with n to infinity, and we have this is bad term, it goes to infinity, but of course this is a wonderful term because we have e to minus s1 eta to power alpha. So that's something nice. But it works only if x1 is not 0. Right? So the question is how many eta to alpha I can get from here. So this is related how many these terms could be 0. But if x1 is 0, I mean measure is not x1 is cannot be 0 because it's on the support of the mu, and mu. So this is not 0. This can be 0. Means x2 is minus x1. Why not? But then x1 plus x2 plus x3 cannot be 0 because x1 plus x2 is 0 and x3 is not 0. So one can see that in the worst situation we can get eta over 2 non-zero terms if n is even, and in the odd case we will always get something like bigger than eta 2 non-zero terms, and this will give me this. So only in the even case I can get non-trivial limit, and we proved that this is actually the moment of the Gaussian of constant time beta t. Okay. Thank you. I think that I can stop here.
I have a couple of questions.
Perfect.
When you, I'm coming back to the beginning of your talk, which is kind of shocking, that the fact that the f disappears in the limit. Is it, what is the borderline for f? I mean, just saying f in L1, any L1, or this breaks down?
They formulate this in the terms of massless, that the Fourier transform of this is massless at 0. I don't remember exactly the formulation, but it is done in the paper by Russo and I think for me f is integrable is just an example, right? But yes, that there's a larger, rather specific class of f.
And then the noise is, can you have space-time noise?
I think this is exactly space-time, what not?
I see, in the Walsh type, the equation, or no?
Well, I don't think it make any difference between. Actually, I think that they formulate in the Walsh language.
But you still get the same result. Huh?
I think that the UN and ZN are the same for Walsh, and I mean that doesn't make any difference. So I prefer this functional analytic approach than Walsh practices.
But I mean, you started from this SPD motivation, and now
Yeah.
you've done all this. Can you go back to the SPD?
Unfortunately, no. No, yes, that was.
But the aim is to get some F's where it doesn't vanish.
What is important from F, right? I mean, what?
But you're not getting zero answers when you want to get some
Yes.
averaging that gives you something non-zero.
So I don't see any paper about such situation.
I mean, you're taking an SPD, which in the linear case has a distribution valued solution, but not a function valued
Yeah.
solution. And you want to formulate a nonlinear version of that and interpret the solution in some way.
Well, that's difficult because, well, I mean, that I cannot. Maybe this is what you should write. T minus s, f of zs. Oh, this is in one language was ys, ds. Y was the solution of linear part. So you have to show that this is 0. So actually,
What does it mean that integrate f of y?
actually, it is 0 in the sense that if you approximate y by in many different ways, you will get 0. Okay, that's in the sense that it is 0. I don't think, I don't know how in the distribution say that f of y is 0 for any, that's not possible probably.
Roger, is this related to what you were saying the other day when you were in dimension 2 and you had a noise that was, say, had some correlation? You said as it approaches space-time white noise, the solution is going to 0.
Yes, yes.
Yeah.
And I think the idea is that it's just a result about the approximation. And the hope would be that for some f's, the nonlinearity in f gets sort of averaged out to produce a term that doesn't have the distribution, but is non-zero. In Russo's case, it's 0.
So you're saying for most f's that go, the limit would go to 0.
Oh, for these f's that are
For these
somehow
f's.
integral. But maybe an f that still gets you a lot of averaging,
I see.
and you'll end up with some constant term. Or
But you've not
plus
yet
a constant.
identified such f's or something.
Yeah, that's what I was asking at the beginning.
Nice point. There are examples of that. This is a very remission equation.
Well,
Hence distribution values. And if you approximate it with some nonlinearities, the nonlinearities get averaged out, and you end up with a linear term, which does make sense. I don't know.
actually what they considered a bit, I mean, they subtract from f a linear part. I mean, f was not originally integrable, but they subtract linear part, and then of course this linear part will survive. But but that was a more complicated picture.
And you will get the same answer if you approximate the Laplacian as opposed to approximating the noise.
Or maybe non-linearity.
Yeah.
I think that this is what I said before, is that it's completely irrelevant what is y. Really. I mean, multiply a nice process in L2 by eta goes to infinity, I will get 0. So if you approximate by, Laplace operator, you will get exactly something like this. So,
Well, if you put projector within f,
yes, but this will change the problem. Yes, of course. That's
The Z has a symmetric distribution,
Yes.
one-dimensional distribution. So what I was saying earlier is that one other way perhaps to try to prove such a central limit theorem is by looking at returns to a small interval of minus epsilon epsilon. Because you don't have exact regeneration there. But if you, I mean, the way people look at these things is you can control the time to come back and then see the integral over this cycle. And if you show that this is the domain of attraction has finite variance, for instance, then that's why we get Gaussian. So it's, I mean, we can replace perhaps ZT by a discrete time random walk with stable increments. And then,
now Yeah.
I mean, this is an approach based on the computation, and I can see why you use trigonometric things because you use it for computation this way. But,
Yes. No, I cannot take also integrable function.
yes, you can take as long as you can pass through some Fourier transform, and then you work with.
No, but then I will get a different scaling, right? No, that's different. No.
You use a little formula for Brownian case effectively, but in the unstable case, can you use at least, for example, heuristic? You can use
We
Ito
haven't
formula
tried.
to derive.
That's probably a good idea, because in this case I can solve easily this equation. If f is this equation I can solve. Yes, that's a possible idea. Exactly.